In the vast, seemingly impenetrable blue of our world's oceans and waterways, a different kind of life thrives. Not of fin and scale, but of concrete and steel. These are the underwater roads and tunnels, monumental achievements of human ingenuity that lie hidden beneath the waves. They are our planet's hidden highways, silent arteries connecting lands once separated by formidable bodies of water. These structures are more than just passages. They are a testament to our relentless drive to explore, to connect, and to overcome the very barriers that nature has placed before us, weaving our world together in ways previously thought impossible. For centuries, we have gazed upon the surface of the water, our journeys dictated by its moods and currents. But with these incredible feats of engineering, we have learned to journey not just across the water, but through it. This impulse to burrow beneath the seabed, to create corridors of light and movement in the crushing dark of the abyss, has fundamentally reshaped our landscapes and our societies. It has allowed communities to merge, economies to flourish, and has pushed the very boundaries of what we believe we can build, creating infrastructure that is as awe-inspiring as any natural wonder. Join me, Ajar, as we take a deep breath and plunge into this extraordinary world. We will explore the colossal efforts required to construct these submerged marvels, from immense tubes floated into place to gigantic machines that bore through the very rock beneath the sea. We will travel through some of the most famous underwater passages on Earth, uncovering the stories of their creation and the profound impact they have on our lives. This is a journey into the depths, not just of the ocean, but of human ambition and innovation. One of the most remarkable methods for conquering the aquatic realm is the immersed tube tunnel. It is a technique born of both brute force and delicate precision. Imagine, if you will, colossal sections of a tunnel, each a hollow, concrete behemoth hundreds of meters long, being constructed not in the depths, but on dry land. Here, in vast, purpose-built casting basins, these segments are meticulously crafted, complete with roadways, ventilation shafts, and all the complex systems needed for a modern highway. It is a process of creation on an almost unbelievable scale. Once a section is complete, it is sealed at both ends with immense steel bulkheads, transforming it into a buoyant, watertight vessel. The casting basin is then flooded, and this monumental piece of infrastructure, weighing tens of thousands of tons, lifts gently from its foundation and floats. It is a surreal sight, a section of roadway adrift on the water. Tugs then carefully maneuver this giant out into the open sea or waterway, a slow, deliberate procession towards its final resting place on the seabed below. Meanwhile, on the floor of the sea, another immense operation has been underway. A deep, wide trench has been dredged, a scar carved into the sediment, precisely engineered to cradle the incoming tunnel sections. It is a challenging environment. Currents and visibility can make this subaquatic excavation a formidable task. Yet, it must be perfect, a foundation prepared in the dark for the giant that is to come, ensuring stability for centuries of use. The floating tunnel section is then positioned with pinpoint accuracy above its designated place in the trench. Ballast tanks within the segment are slowly filled with water, and with immense control, the colossal structure begins its descent. It sinks, slowly and gracefully, through the water column, guided by powerful cranes and GPS technology. It is a descent into the quiet dark, a piece of our terrestrial world being delivered to the abyss. Once resting in the trench, it must be joined to its neighbor. This is perhaps the most critical moment. A massive rubber gasket, known as a GINA gasket, creates an initial seal between the two sections. The water trapped in the small gap between the bulkheads is then pumped out. The immense pressure of the surrounding sea then forces the new section against the existing tunnel, compressing the gasket and creating a perfect, permanent, watertight seal. After the sections are joined, the temporary steel bulkheads can be removed from the inside, revealing a continuous open passage. It is a moment of triumph, where separate floating behemoths become a single unified structure. The process is repeated, section by section, like assembling a colossal jigsaw puzzle on the seabed, each piece adding another length to this emerging underwater highway. The trench is then carefully backfilled, burying the tunnel beneath a protective layer of rock and sand. This not only secures the structure against the powerful forces of the sea, but also helps to restore the natural seabed environment. The tunnel becomes one with the seafloor, an artificial feature integrated into the submarine landscape, hidden from view but teeming with life of a different kind. This method, though complex, is favored across the globe for its versatility. It is particularly suited for wider, shallower bodies of water where boring deep beneath the seabed is impractical. It allows for the construction of tunnels with multiple lanes and complex internal geometries, all built in the controlled environment of a dry dock before being submerged. Consider the Øresund Tunnel between Denmark and Sweden, or the Busan Gyeonggi Fixed Link in South Korea. These are prime examples of the immersed tube method's success. They stand as silent, submerged monuments to this incredible process, where massive structures are floated, sunk, and seamlessly joined in the deep. It is a dance of engineering giants, a ballet of concrete and water. The immersed tube method demonstrates a profound understanding of physics, materials science, and the marine environment. It allows us to build not by fighting the water, but by using its own properties, buoyancy and pressure, to our advantage, creating passages that defy the very element they are submerged in. For journeys that must venture deeper, through solid rock far beneath the seabed, a different kind of creature is required. This is the realm of the tunnel boring machine, or TBM. These are not simply machines, they are subterranean leviathans, cylindrical factories that grind their way through the Earth's crust. Some stretch for hundreds of meters, a moving assembly line of excavation, reinforcement, and construction, all happening simultaneously at the tunnel face. Their work is unseen, unfelt, a silent advance through the dark. The TBM's journey begins in a massive launch shaft, dug on one side of the waterway. From here, it is assembled piece by colossal piece, a mechanical beast being prepared for its long, slow hunt. The most critical part is the cutter head, a giant rotating disc studded with incredibly hard cutting tools. This is the face of the machine, the part that will meet the rock, grinding it into manageable fragments known as spoil. As the cutter head spins, hydraulic rams thrust the entire machine forward with immense force, pressing the cutters against the rock face. The rock fractures and breaks away, collected by scoops on the cutter head and transported back through the machine on a system of conveyor belts. This continuous process of excavation allows the TBM to advance, inch by painstaking inch, through even the hardest geological formations. Life for the crew aboard a TBM is like that of submariners or astronauts. They work in a confined, artificial environment deep underground, for shifts that can last 12 hours or more. They are entirely dependent on the life support systems of the machine, which provides fresh air, power, and communication with the surface. It is a world unto itself, a bubble of human activity moving slowly through the silent, pressurized darkness. Behind the cutter head, another marvel of automation takes place. As the TBM moves forward, it leaves behind a perfectly smooth circular tunnel. A robotic erector arm picks up precast concrete segments, brought to the front on small trains, and fits them together to form a complete ring lining the tunnel wall. This provides immediate structural support, protecting the tunnel from the immense pressure of the rock and water above. The space between the newly placed concrete lining and the excavated rock wall is then filled with grout, a type of cement mixture. This is injected under high pressure, filling any voids and locking the tunnel lining securely in place. It ensures the tunnel is not just a hole, but a permanent, integrated, and completely watertight structure, capable of withstanding the colossal forces pressing in from all sides for a century or more. Navigating a TBM is an art of immense precision. Guided by lasers and GPS systems, the operators must steer this giant machine along a predetermined path with millimeter accuracy. They must constantly analyze the geology ahead, adjusting the speed, thrust, and cutter head rotation to deal with changing rock conditions, from soft clay to hard granite, and even unexpected pockets of water or gas. The Channel Tunnel, linking the United Kingdom and France, is perhaps the most famous testament to the power of TBMs. Two teams, one from each country, bored towards each other under the English Channel. The moment they met in the middle, a tiny pilot hole drilled through to connect the two tunnels, was a moment of historic triumph, a handshake deep beneath the sea, uniting two nations. Similarly, the Seikon Tunnel in Japan, the world's longest and deepest rail tunnel with a significant underwater section, was bored through a notoriously challenging volcanic fault zone. It required decades of effort and pushed the boundaries of TBM technology, a heroic struggle against some of the most difficult geological conditions imaginable. The bored tunnel represents a brute force assault on the Earth itself. It is a method for when there is no other way, for crossing deep channels or traversing unstable seabeds where other techniques would fail. These great borers, these mechanical worms, allow us to create passages in places we have no right to be, forging connections through the very heart of the planet. Not all underwater journeys require a plunge into the deep abyss. For tunnels that lie in shallow waters, close to the shoreline, a more direct, almost agricultural method is often employed, the cut and cover technique. As the name suggests, it is a process of excavation and restoration, a temporary reshaping of the land and seabed to install a permanent passage beneath. It is actually one of the oldest and most straightforward methods of tunnel construction. The process begins by creating a dry work area in the water. This is typically achieved by building cofferdams, which are temporary watertight enclosures. Sheet piles, those long interlocking sheets of steel, are driven deep into the seabed to form a barrier. The water within this enclosure is then pumped out, exposing the seabed and creating a construction pit, an island of dry land surrounded by water. With the worksite secured and dry, excavation can begin in earnest. Heavy machinery, such as excavators and bulldozers, are brought in to dig a large trench down to the required depth for the tunnel. The scale of this earth-moving operation can be immense, a deep channel carved into the earth where water once was, its sides carefully supported to prevent collapse. Inside this open trench, the tunnel structure itself is built. This is often done using traditional construction methods, a technique known as bottom-up construction. A concrete foundation slab is poured, followed by the walls and finally the roof. Steel reinforcement bars are meticulously placed to give the concrete the strength it needs to support the immense weight that will eventually be placed upon it. The tunnel is constructed piece by piece within the trench, kind of like building a long, rectangular concrete box. This in-situ construction allows for a high degree of control and inspection, ensuring every joint is sealed and the entire structure is completely waterproof. A thick membrane is often applied to the outside of the completed structure, an extra layer of defense against any potential water ingress. Once the tunnel structure is complete and has been thoroughly waterproofed and inspected, the process of covering begins. The trench is carefully backfilled with the earth that was originally excavated. The material is replaced layer by layer, compacted to ensure stability, until the tunnel is completely buried and the original ground level, or seabed level, is restored. After the backfilling is complete, the cofferdams are removed. The sheet piles are extracted and the water is allowed to flow back over the area. The land, or seabed, is returned to its former state, with little or no visible evidence on the surface that a massive concrete structure now lies buried just a few meters below. The passage is hidden, integrated back into the environment. This method is particularly common for tunnel approaches near the coast, where a bored or immersed tube tunnel transitions to an onshore road or railway. It is also used for crossing small rivers or canals. The simplicity and cost-effectiveness of the technique make it an ideal choice for these shallow water applications, where the disruption to the surface is temporary. You can see this technique in action at the entrances to many famous tunnels. The landward sections of the Øresund Tunnel, for example, were constructed using cut and cover before the main immersed tube section begins its journey under the sea. It provides a seamless transition from the open air into the subterranean world. While perhaps less dramatic than its deep water counterparts, the cut and cover method is a vital tool in the engineer's arsenal. It is a testament to a different kind of ingenuity, not of conquering the deep, but of carefully and temporarily displacing the shallows to create lasting infrastructure, before returning the environment, as closely as possible, to how it was found. Across our planet, these underwater arteries form a network of extraordinary connections. Let us journey through some of the most famous. Our first stop is perhaps the most iconic, the Channel Tunnel, or Chunnel. Linking Folkestone in the United Kingdom with Coquelles in France, it is a 50-kilometer-long railway tunnel, with 38 of those kilometers running deep beneath the English Channel. It is a true symbol of European unity, a project of such scale it was named one of the 7 wonders of the modern world. Next, we travel to Japan, to the remarkable Tokyo Bay Aqua Line. This is not just a tunnel, but a stunning hybrid of bridge and tunnel. It crosses Tokyo Bay with a 4-kilometer bridge that gracefully descends onto a man-made island called Umihotaru. From this island, which serves as a rest stop and viewing platform, the crossing continues as a 10-kilometer tunnel, the fourth longest underwater road tunnel in the world. This design was chosen to avoid disrupting shipping in one of the world's busiest sea lanes. Our journey now takes us to Scandinavia, to the Øresund line. This marvel connects Copenhagen, Denmark, and Malmö, Sweden. Much like the Aqua Line, it is a combined bridge and tunnel system. An 8-kilometer bridge, a stunning piece of architecture in its own right, carries road and rail traffic from the Swedish coast to the artificial island of Peberholm. Here, traffic descends into the 4-kilometer-long Drogden Tunnel, an immersed tube tunnel, to complete the crossing to Denmark, keeping the flight path to Copenhagen Airport clear. We return to Japan to witness another colossal achievement, the Seikon Tunnel. For over 3 decades, it held the record as the longest and deepest railway tunnel in the world. It stretches for 53.8 kilometers, with a 23.3-kilometer section running 100 meters beneath the seabed of the Tsugaru Strait. Built to provide a reliable link between the islands of Honshu and Hokkaido, it was a response to the dangers of ferry travel in a region known for its typhoons, a monument to perseverance. Our final destination takes us to a remote archipelago in the North Atlantic, the Faroe Islands. Here, we find the Eysturoyartunnelen, a tunnel that is as much a work of art as it is a piece of infrastructure. This 11-kilometer sub-sea tunnel is famous for featuring the world's first underwater roundabout. The central pillar of this roundabout is a stunning sculpture by a local artist, illuminated with ethereal blue light, transforming a daily commute into a truly otherworldly experience. Each of these structures tells a unique story. The Channel Tunnel speaks of connecting historic rivals. The Aqua Line and Øresund Line show a clever compromise between the needs of sea and land transport. The Seikon Tunnel is a tale of ensuring safety and reliability against the forces of nature. And the Eysturoyartunnelen demonstrates that even the most functional infrastructure can possess a profound and moving beauty. They are more than just concrete and steel. They are expressions of national ambition, of economic necessity, and of the unceasing human desire to overcome physical barriers. They have redrawn maps, not by changing the land, but by burrowing beneath the water that separates it, creating invisible but powerful bonds. From the busy English Channel to the serene waters of a Faroese fjord, these tunnels accommodate millions of journeys every year. They are the silent, hidden workhorses of global transport, their entrances like mouths on the landscape, swallowing traffic and delivering it, safe and dry, to a distant shore. The engineering challenges overcome in each project were immense. The Channel Tunnel's boring machines navigated treacherous chalk marl. The Øresund Tunnel's immersed tubes were placed in a busy shipping channel with pinpoint precision. The Seikon Tunnel battled volcanic rock and high water pressures. Each is a victory of calculation and courage. These underwater wonders are a powerful reminder that the world's great waterways are not impassable barriers, but simply challenges waiting for a solution. They stand, or rather lie, as proof that with vision, collaboration, and extraordinary engineering, we can forge connections in the most unlikely of places. Why do we embark on these colossal, expensive, and often perilous undertakings? The reasons for building these underwater passages are as deep and compelling as the tunnels themselves. The most immediate and obvious benefit is the dramatic reduction in travel time. Journeys that once took hours by slow, meandering ferry can be completed in mere minutes, transforming daily commutes and regional travel. This newfound speed and efficiency have a profound economic impact. By replacing weather-dependent ferries with all-weather tunnels, we create uninterrupted logistical chains. Goods, services, and people can move freely, 24 hours a day, 365 days a year, regardless of storms, fog, or ice. This reliability is the lifeblood of modern commerce, fostering trade and integrating regional economies as never before. There are also significant environmental advantages to consider. While the construction process is intensive, the long-term operation of a tunnel can be far greener than the alternatives. It eliminates the need for fleets of fossil fuel-burning ferries, reducing air and noise pollution. By moving traffic underground, it also preserves the natural beauty of coastlines and sensitive marine ecosystems on the surface. Furthermore, these subsea links offer unparalleled resilience. They are immune to the weather that can halt ships and even close bridges. In a world facing more extreme weather events due to climate change, having infrastructure that is protected deep beneath the waves is a powerful strategic advantage. It ensures that vital connections remain open even when the surface is in turmoil. Tunnels can also solve complex spatial problems that bridges cannot. In busy shipping lanes, a bridge high enough to allow the world's largest vessels to pass would be astronomically tall and expensive. Near airports, a bridge could interfere with flight paths. A tunnel neatly ducks under all these obstacles, providing a seamless crossing without disrupting activities on the surface. Consider the social impact. For island communities or regions separated by fjords and bays, a tunnel can be a lifeline. It connects people to hospitals, schools, and jobs. It ends the isolation that can define life in such places, weaving remote communities into the fabric of the nation. The Eysturoyartunnelen, for example, slashed the commute time between the Faroese capital and its second-largest town from over an hour to just 16 minutes. They also represent a pinnacle of safety. Modern underwater tunnels are equipped with state-of-the-art ventilation, fire suppression, and surveillance systems. They provide a controlled environment, free from the hazards of open-water navigation, crosswinds that affect bridges, and the risk of collisions that ships face. They are, in essence, one of the safest ways to travel. The drive to build these structures also fuels innovation. Each new project pushes the limits of material science, robotics, and geotechnical engineering. The challenges of boring through difficult geology or placing immense structures on the seabed force us to develop new technologies and techniques that can then be applied to other fields of construction and exploration. They are long-term investments in the future. A tunnel built today will serve generations to come, a permanent piece of infrastructure that fundamentally alters the geography of possibility for a region. The initial cost is high, but the economic and social benefits, accrued over a lifespan of a century or more, are immeasurable. Ultimately, the reason we build underwater is the same reason we build anywhere: to connect, to bring people and places closer together, to overcome the natural divisions of our world in the pursuit of a more integrated, efficient, and resilient society. These tunnels are not just about transport. They are about building a more connected human world. We have journeyed through the dark, pressurized world beneath the waves and have seen how human ambition has carved passages of light and connection through it. These underwater roads and tunnels are far more than just convenient shortcuts. They are monuments to our ability to solve monumental problems, to reshape our world not through domination of nature, but through a deep and clever understanding of it. They represent a quiet, constant, and reliable heartbeat of our global infrastructure, hidden from sight but essential to our modern lives. The importance of these submerged lifelines will only grow as our world becomes more interconnected and our need for resilient infrastructure becomes more acute. The future of this technology is as deep and vast as the oceans themselves. We are now seeing proposals for tunnels that are longer, deeper, and more ambitious than ever before. Imagine floating submerged tunnels, anchored to the seabed but suspended in the water column, crossing deep Norwegian fjords. Think of intercontinental connections that could one day link entire landmasses. The drive for innovation continues, pushing us towards solutions that are not only more efficient, but also more in harmony with the natural world. By placing our transport arteries beneath the surface, we leave the land and sea above free for nature and for ourselves. These incredible structures embody the very best of human endeavor. They are a fusion of innovation, a commitment to environmental stewardship, and a quest for resilience in the face of a changing planet. They teach us that sometimes the best way forward is not over, but through. As we continue to build and connect our world, we will undoubtedly look to the silent, submerged world beneath the waves for answers, creating a future that is deeper, stronger, and more connected than ever before.
Ready for a history adventure? Join our community. Subscribe to World History, smash that like, share with friends, and drop your thoughts below. Let's make history together. See you in the comments.